Could you even get a machine that's as powerful as a cloud?
You can, but it's very, very expensive. And so there's a cost efficiency here. You're paying for only what you use. You don't have to upfront say, I need this X amount of dollars server so that I can run my analyses. You pay as you go with the cloud.
Hello, everyone, and welcome to another episode of Eyes on Earth. We're a podcast that focuses on our ever-changing planet and on the people here at Eros and across the globe who use remote sensing to monitor and study the health of Earth. I'm your host for this episode, John Holt. Satellite imagery is everywhere. We see it on TV news and weather coverage, in our Twitter and Facebook feeds, and on our phones' mapping apps. The data behind that imagery, though, is nothing like a screenshot. It's comprised of tiny packets of data digitally manipulated to resemble, say, the surface of the Earth, a swirling storm system, or a map of urban growth. These are huge files. A single Landsat scene of around 115 square miles is well over 2 gigabytes, larger than some full-length films. It takes a lot of computing horsepower to download and analyze large satellite datasets, particularly when the goal is to answer questions about change over time. That's one of the reasons why remote sensing scientists are increasingly turning to cloud computing, which allows users with cloud accounts to analyze, visualize, and interpret satellite data without downloading it and storing it locally. It's also why the USGS created a cloud-optimized format for Landsat data with Collection 2, and why NASA's Land Processes Distributed Active Archive Center, or LPDAC, is developing tools to help scientists learn how to use the cloud. Joining us today to talk about cloud computing are Stephanie Cogoni and Aaron Fries. Cogoni is a remote sensing scientist and contractor at Eros who's used the cloud to analyze decades of satellite data to study water use across the United States. Fries is the science coordination lead for the LPDAC, which is located at Eros, where he works on tools that help users get started with the cloud. Stephanie, Aaron, thank you for joining us.
Thank you for having us.
Thank you, John.
First, let's talk a little bit about the cloud. What is it, and how is it useful for working with satellite data? Aaron, do you want to take that one?
The cloud is essentially servers and compute resources that you or anyone can access over the internet. Cloud computing delivers scalable, on-demand, pay-as-you-go access to pools of compute resources. In addition to having the servers that store data, massive amounts of data, you have resources like RAM and GPUs and CPUs that allow you to perform your analysis. The marrying of satellite data being stored in the cloud is perfect. We don't have to rely on your local machine and the resources that come with that to perform your analysis, nor do you have to download massive amounts of data and have the infrastructure to store that. Now you can log into a cloud account and access those data where they are saved and perform your analysis next to the data. Having on-demand resources gives you the ability to perform at-scale analysis.
So when you say at-scale analysis, can you give us a real quick definition of what you mean there when you're saying that?
Oftentimes, you have to narrow your research area of interest down. And so rather than focusing on South Dakota, I can scale my research out to the United States or even global scale. And so I'm not restricted by my resources to perform these analyses.
In other words, the cloud behaves like a great big supercomputer on the user side, and instead of needing to have a giant powerful machine, you can rent time and do all the work without having to do the downloading or pay for that hardware. Correct me if I'm wrong here, but anybody can access this quote-unquote supercomputer anywhere in the world. It doesn't matter where you are, whether you're at a fancy research facility, a fancy university, or somewhere much smaller, like your own house. You can use the cloud, right?
Totally. Yeah. Anywhere you have internet access, you're not restricted by your location, but also by the device that you're using. You don't need a massive desktop. I can run a workflow from a cell phone.
You don't have to have a fancy computer to get in there, and you don't have to have a fancy computer to work with the data and work at scale. So Stephanie, let's turn to you now. Tell us a little bit about your research focus, which is evapotranspiration. First, tell us what is evapotranspiration and how have you used satellite data and the cloud to study it?
Evapotranspiration, or short ET as we call it, since it's quite the word, is a combination of evaporation and transpiration. And evaporation is usually that comes from soil, and transpiration comes from plants. It's an important part of the water cycle. About 60 to 70% of the water received by precipitation in that cycle is really recycled back into the atmosphere in that way.
And it's invisible, right? So the 60, 70%, you can't just see it. You can see a rain gauge, but you can't see this, right?
Exactly. So that's what makes it a little bit difficult to grasp or to model, since you're dealing with water vapor, what is usually invisible to you.
Okay. So how do you use satellite data to track ET?
We know that if a plant is healthy, it produces a lot of ET. If it has enough water available from the soil in form of soil moisture, and if there's enough energy through sunshine to convert that water back into water vapor. And ET, therefore, is also a measure of how healthy a vegetation is. Or you can see if the vegetation would be under stress by drought conditions or even a fire. ET can tell how much irrigation water is needed to keep, let's say, a field of crops healthy throughout the growing season. So we use the remote sensing data, let's say, for example, from LPDEC, from Aaron's group, and from other sources like weather data sets like wind, speed, etc., to estimate the ET values at various scales. And that's from global extent for drought monitoring purposes. You can also do field scale using Landsat imagery, for example, to determine the water used or the irrigation water need of a field. So ET is quite scalable from bigger basin-wide applications down to a field scale application to actually look at really the plants itself and how healthy those are.
Tell us how cloud computing has been valuable in that work, because you talked about basin-wide and even global scale. You were even able to look at 150 years of data using cloud computing.
Yes, John, we did. We received the task to create 150 years of ET data for the Delaware River Basin on the East Coast from like 1950 to 2100, and the deadline was about 9 months. I knew from previous model runs and experience that would not be currently possible with the tools I had. Just for the Delaware River Basin would have taken probably about 5 months for one run to finish. So therefore, we turned to the cloud because okay, let's try it. It's a new concept to the team, to us. Let's just try, jump into it and see what we can do with it. And then, of course, using the cloud computing and bucket storage, that provided us then really the resources we needed to complete the task. After we got the code and everything ready on the cloud, we were able to process 150 years in about 5 days. What enabled us for the first time to run the model over and over to actually debug every little bug that we had. We also could evaluate the estimates, and we could change the input variables into the model and run comparisons, and we could do it over and over and over because it would take 1 work week to do that instead of 5 months to do it. At the end, we could provide a high quality product to our customers and to the stakeholders.
If I'm going to summarize here, it sounds like you could have potentially run this 150-year model using the compute resources that you had, but it would have taken you 5 months, and that wouldn't have really given you any time to deal with problems, like you say, fix the code. So you turned to the cloud and you cut it from 5 months to 5 days?
I couldn't believe it myself, and I wish I would have even used it earlier, but it's sometimes a little bit of a hurdle if there's new technology involved. But I really think it's really worth it for researching it or investing into it and getting to know it a little bit as a scientist, not just as a computer person.
I want to stay on this point for just a second. How much of a learning curve are we talking about? Did you have to spend 2 or 3 months at coding boot camp or something to figure this out? I mean, how much of a time commitment was involved? Because I know that is a thing that is kind of a hurdle for people.
The main thing there we really needed to do, we needed to adjust the code to be able to run on the cloud. And that took us 1 or 2 months. And then I would say it was another month to learn your way around the cloud, learn the new terminology, and just get over the fear that new technology brings. It is really not so different than other software. It is just on a bigger scale.
Aaron, let's turn back to you. When NASA polls its satellite needs working group about research practices, it still finds that a majority of users download data rather than using the cloud. And it's my understanding that the LPDAC is working to both explain the benefits of cloud computing and help scientists learn how to use it. There's something called Earth Data Cloud Cookbook, which is pretty entertaining. But there are a lot of tutorials and resources out there. Tell us a little bit about those efforts.
That download model has been the method of choice for a number of years because it was really the only thing that we had. But with the cloud, there's efficiencies to be gained there. No longer do you need to fill up hard drives with kind of these dark repositories of data. The LPDAC has many efforts going. For a number of years now, we've developed these Jupyter notebooks that kind of give you a feel for working with data. We've started incorporating our cloud data, showing that it's not that big of a jump to take this Python Jupyter notebook and execute it against a data set that is in the cloud. The EarthGated Cookbook is part of a collaboration that NASA has with OpenScapes. We have a number of NASA DACs that are involved in this effort. The LPDAC involves land processes. There's other DACs that have a community of ocean or atmosphere or cryosphere users. And so we're bringing all these groups together and starting to identify commonalities in our resources and see where we can collaborate and build on these tutorials so that we can have more interactive, more cross-DAC experience with our data.
Let's talk about the benefits and drawbacks. What might those be? Aaron, why don't we stay with you on that one?
Well, the first thing now is what Stephanie just talked about, being able to do big data analysis in a much shorter amount of time and being able to iterate too. There's a lot of tinkering that goes on to come to a model that is representative of a system.
When you say iterate, you're talking about the fine tuning that needs to happen.
Absolutely. Yeah.
Okay.
Stephanie said that they had a 9-month deadline. There's really no room for mistakes if you have a model that's taken 5 months to run. But if you have something that you can run in a week, then you can fine tune and rerun, validate, rerun, and do the scientific method on those.
It's not just the ability to scale up and do these large data sets, but it's also the ability to fine tune and really just improve the products that you are creating.
Absolutely. Yep. And then also another benefit is being able to really combine data that was never able to be combined when we were working from local machines because of the restrictions of resources of storage. With that data in the cloud, you can start combining data and gaining new insights that were not achievable when we were working from local machines. Drawbacks may be a little strong, but yes, there's cost factors, of course. It is a pay-as-you-go model. And so on the best of days, you could be paying exactly for what you used on that machine. Errors occur and some people leave machines running. And so that when those machines are running, you're paying for that resource. There is definitely a learning curve. I think more and more there's applications that are making their way to the cloud so that those who are more familiar or more comfortable working from like a graphical user interface will have that ability. But right now, those who are working in a scripting environment, this is really a sweet spot for them. The learning curve for those individuals is not necessarily understanding Python or R, but understanding the behind the scenes kind of cost calculations.
Here's one for both of you. What kinds of questions can we ask with cloud computing that wouldn't have been possible 10 or 20 years ago?
I see the value in doing more long time series analysis, like the 150 years that we did. So we were looking backwards into time, also into the future. And we can do that maybe not just for a small area or small basin, but we could do that for regions all around the world. And especially since remote sensing data is globally available, that would be a great benefit. If we would study more of the globe and the different processes and how everything is connected, and if we make changes to the environment, we could learn from those findings we do globally and maybe apply it locally.
Aaron, what are you hearing about? What are you hearing people talk about?
There's now the ability to get more ideas, the open inclusiveness of the cloud. Anyone who has an internet connection can access the cloud. So this really opens a door for more ideas to come in, ideas from individuals, groups who really never had a seat at the table whenever they were doing these types of scientific research because they didn't have the resources to actually contribute. Also, now it's easier to share. The process is more transparent. It's more open. It's community driven at times. And so doing reproducible science is actually achievable now. No longer do we have to do the science in our lab, write up an article, publish that. Sometimes it's behind a paywall. Now, we're definitely moving to a more transparent, a more open paradigm for doing science. Now I can bundle up my algorithm, the pointers to the data sets that I use, and I can ship that off or make it available to the community, and they won't have to reinvent my procedure. They can just open it up, deploy that container, and then they can make adjustments as they see fit.
Any closing thoughts from either of you? Stephanie, why don't we start with you since we just heard from Aaron?
Cloud computing really is a great tool in your toolbox, but it shouldn't really be seen as the only tool because we sometimes get like, oh, then you just have to use the cloud. And I would not really necessarily agree with that. But together with your local laptop, with your computer, along with the cloud or even high performance computing for the heavy processing, we can really do great science here at Eros and around the world and help to make a positive impact on the pressing issues of our time, like including the droughts, floods, fires, and even land use change.
I personally am excited about the prospect of innovation. I think we've seen the tip of the iceberg. I'm thinking it's just going to gain momentum and we're going to see some really neat science coming out of this migration to the cloud.
We've been talking with Stephanie Cagoni and Aaron Fries about using satellite data in the cloud. Stephanie, Aaron, thank you for a fascinating conversation.
Thank you, John, for having us.
Yeah, this was great.
And thank you to the listeners for joining us as well. You can find all our shows on our website at usgs.gov/eros. That's usgs.gov/EROS. You can also find Eros on Facebook and Twitter to see the latest episodes, and you can find us on Apple Podcasts or Google Podcasts. This podcast is a product of the U.S. Geological Survey, Department of Interior.